So I'm going to give a demonstration of some of the experimental work I've been doing with simulating engine crank triggers on the bench. I put this together in order to start doing some ECU testing and seeing what the feasibility of actually generating valid engine crank triggers or crank trigger simulations are from a completely bench setup without requiring an actual engine or some type of real-world rig. What I've got in front of me is an Atmel STK500, which is kind of your typical Atmel AVR development kit. I've got a Atmega 16 running at 3.7 megahertz and change. Hooked up to that is a run-of-the-mill Tektronix TDS 2024B with channel 1 and 2 hooked up to the Atmega 16's port B bits 0 and 1 respectively. So what I've put together is effectively it's an edge scheduler. It allows you to generate arbitrary waveforms across 8 different outputs. And by arbitrary, you pretty much can make as many edges in your signal, recurring signal, as you want, limited only by RAM. So let's give a quick demo. So I'll turn this thing on. So let's start off with doing a 36 teeth wheel with 1 missing at 3600 RPM. Initialize. You just saw it get pulled low. And do 36 teeth with 1 missing. And let's kick this thing off. So I've added in a second kind of sync pulse just to keep finding things on the oscilloscope easier. Let's go back, actually. So here you can see the 2 sync pulses corresponding with the 2 missing teeth gaps. And we're running right now at around 59.7594 hertz on the sync, so that's 3585. So there's a little bit of an improvement that could be made there with regards to resolution and hitting our marks. You can kind of make out a bit of a clock jitter in some of the teeth as well. I think that's occurring because the oscillator I've got on this board is actually the internally derived one. Going to an external 16 megahertz crystal would probably fix some of that waver you can see. But again, it shouldn't affect the actual testing for initially. So let's go ahead and generate something a little different. Let's go to the same speed, 3600 RPM, a 60 minus 2 wheel. You see we just upped our tooth count, but our frequency stayed the same because we're still running the same RPM. Again, there's our 2 teeth missing and the rest of our teeth. So it looks like about 3 degrees per edge. A 60 tooth wheel, so 6 degrees total per tooth, periodic. You can use this to generate pretty much any type of triggering output you want, or simulation I should say. You could do something akin to a Series 4 or Series 5 RX-7 crank angle sensor. So generating something like that would be pretty trivial. Let's do 6,000 RPM with 2 sync teeth and 24 event teeth running at half engine speed. So here you can see we're at 99 hertz per sync tooth. We got 2 per cam revolution, so that puts us at 6,000 RPM. You can kind of go in and look at the teeth. It's about 6 degrees wide per tooth. Some improvements that could be made are, I believe in the RX-7 CAS, the actual sync tooth sits in between 2 of the reference teeth, so that could be a kind of improvement made. And that's fully supported, just a matter of programming that in. So the other great thing you can do with this is you can do kind of arbitrary pattern generation. So let's say that I want to make a pattern that no one's ever seen before. I can quickly go through and say, okay, at 8,000 RPM, I want to make a pattern that has, it is 20 degrees high, low for 20 degrees, high for 20 degrees, and then low for 300 degrees. So there we go. So let's zoom out a bit. So now we've just constructed a pattern that doesn't exist in the real world. I've got an extra sig tooth in order to make the triggering simple, but obviously it's you can do kind of any combination you want. Yeah, so yeah, this is what I've been working on. Thanks.